Welcome to the GIS lecture about digital terrain modeling. Learning goals for this lesson are that you learn how terrain data is collected and how terrain is digitally represented in a GIS and how you can analyze digital terrain. What is the interaction between terrain and climate change? There are many important interactions. So first of all, topography will affect rain and snowfall. Secondly, topography creates distinct wind patterns. Topography also has an influence on water runoff and erosion. And the higher you get in terms of elevation, the cooler the temperatures are. Also, the orientation of slopes, is it south facing or north facing, has an important impact on microclimates and on the vegetation on these slopes. So, in conclusion or in summary, microclimate, but also climate change and terrain are closely linked and interacting with each other. And you can see that, for example, at the tree line in the mountains. We can already observe that with climate change, trees are growing in higher and higher elevations. Another example, the average snowfall or average snow line, the elevation from where you have snow for skiing, for example. Over the last few decades, this snow line has gone up and up. So now we have former skiing areas that are not, that don't have enough snow anymore for skiing, and we have to go higher and higher. So all these are examples for the interaction between terrain and climate change, and therefore it's important to know how we get digital terrain in our GIS and how to work with it. Digital terrain is a representation of the real world. The easiest representation is through contour lines, and you know contour lines from walking. If you have a hiking map, a walking map, these are usually drawn with contour lines, giving you an idea how steep your walk will be. We are using contour lines in GIS as well, but we also have 3D surfaces, and these allow much more complex analysis. But first of all, we have to get the terrain data into our computer. We have to survey the terrain. And surveyors are usually using a total station put onto a point where we have the coordinates and the elevation, and then measuring through distance and angle to other points the elevation and location of that point. That's the classic conventional way. Then another way is with a GPS, a global positioning system. We have satellites for the GPS system flying in orbit. And there are now new systems, for example, Galileo by the European Union. And with these satellites, we can calculate our position and elevation. This process is called trilateration. It's a type of triangulation, and you need to have connection to at least 4 satellites. But with all the satellites today, we often get connection to 20 or more satellites. And the more and the better spread out these satellites are, the higher our precision. So your GPS receiver, and you have that in a normal smartphone these days, your GPS receiver is calculating the distance to the satellite from the little time delay in the signals. And with a minimum of 4 distances to 4 different satellites, it can calculate your exact position in terms of location and elevation. Other ways to collect terrain data. We can use remote sensing. These are satellites, planes, or today drones to scan and survey our surface. First of all, these drones, for example, they're just a flying tripod. But the key is in the sensor. And we have different sensors. We have RGB sensors, a camera, we have radar sensors, we have multispectral cameras, and we have laser scanning. Let's start with the laser scanner. You could imagine that a laser scanner is a scanner that is flying over a surface. Let's use this laser pointer, and every 1 meter, the laser scanner is sending out a laser beam and then collecting the reflection of this beam. And the reflection is giving the exact distance and angle to the ground point and the color of that point. And by this way, you collect millions of points with the exact location and color, and you get a model like the model in the bottom right. This is not a photo, it is a point cloud made of millions of points with each individual color coming together to a representation of the surface. Another cheaper way is through photogrammetry. If you're recording a video with a lot of images that overlap, the computer can relate these images to each other and identify identical points in these images. If you also know the exact location of at least one, better 4 or 5 of these points, it can be georeferenced and put into the context of a coordinate system. And the result is also a point cloud, even cheaper and faster than using laser scanner, although not quite as precise. And here is an example of a surface model derived from such a laser scanning campaign. And you can see the trees, the buildings, these are all derived from the reflection of the laser scanner laser beam. No matter which of these methods you're using, you will get a lot of points. You can now calculate a 3D surface, a 3D mesh from these points. This calculation is based on a triangulation, and this specific triangulation was developed by a Russian mathematician, Delaney, so we call it Delaney triangulation. And here this slide is showing that it's preferable to have rather even triangles. The triangles shouldn't be too one side, not too one-sided. One more thing to consider. In a digital terrain, you cannot represent points that are on top of each other. For example, a wall, a cliff, or a tunnel. So we have to represent a tunnel, a wall, etc. in a different way, and that's represented by break lines. And then these break lines are integrated into the digital terrain model afterwards. But here we have a typical situation, points describing the surface, the terrain, and then a break line for a cliff in this terrain. If we are now applying the Delaney triangulation to this, it will calculate a network of little triangles that is approximating this surface. And if you think about it, think of a fisher net. What's the best way to approximate an uneven surface? You're draping a net over this surface. And that's what we are doing here in the computer. We are draping our little mathematical fisher net over the uneven surface. And this becomes our digital terrain model. So in summary, we have 3 different options to represent terrain. We can represent it through points seen in the top left. We can represent it with contour lines, but we can also represent terrain as a 3D surface. In this case, a network of triangles. Therefore, it's called a triangular irregular network, or short TIN. And these tins are also used in other applications, for example, in computer games. It's the best and most efficient way to represent a 3D surface. Perhaps the data you need is already collected, so there are some open data sources for terrain. A global data source that is available to everyone is NASA, the American Space Agency, and they provide terrain data for the whole globe with a resolution of 30 meter. That means you have an elevation point every 30 meter. From local surveying institutions, you can data as precise as 1 meter resolution, so one elevation point every 1 meter. You would have to look into your local surveying institutions or contact them. But globally, you can start working with the NASA data, which has a 30-meter resolution. So try that out, look for terrain data, and I will see you for the next lesson.